connecting to the cloud, and then I do the share again. I don't know.
It's recording movie, all fine. All looks good.
Okie dokie. So should we start? Good. Okay, so this is about constraint solving. It's a bit technical, but feel free to stop me at any time. There's a lot of research here. It's like covering, I guess, at least 30 years of research, and I use many slides from many sources. So the first things we need to discuss is the SAT problem. So I guess if you are in the US, you think of SAT like the SAT exam, right? But here as computer scientists, we think of the satisfiability problem. So you're giving a formula, and this formula is parametric by the variables like A, B, and C. And this formula is Boolean. It says either A or B holds and not A or not B and C. And we are trying to find if this formula can be true, if it's satisfiable. And we are searching for basically for all the values of A, B, and C. And we are interested in this case, both in the case that it's satisfied and it's not satisfied, both of the case. And so we are interested in both yes and no answer. And this is considered a very hard problem because if you only have n variables, then you have 2 to the n values. And later on, we will consider actually cases that the values are not Boolean. So this will be even infinite values. And so this is the SAT problem. Questions so far? You have. And just to give you like a simple example, so A can be either 0 or 1. So this is basically the enumeration of the values. A can be either 0 or false and true, and B also can be false or true, and C can be false or true. And if A and B and C are all false, then the value is false. Because you see, this is false and this is false. But for example, if A is 0 and B is true and C is either 0 or 1, then this formula is true because if A if B is 1, then this formula is true, and then this formula is also true. So this is a satisfiability problem. I guess you all heard about it. And probably what you were told if you are studying computer science is this is a very hard problem. And it's a problem which is hard to approximate. A lot of things, you heard a lot of bad things about this problem. But in fact, it's not true. What we know in practice, and this is a lot of progress has been done here, that in fact, in many cases that we don't understand theoretically, this problem is actually pretty easy. We can solve it in huge formulas, both for finding satisfiability and for finding unsatisfiability. So the joke is that somebody say that in order to show that the problem is hard, you show that you can solve a SAT problem with it. But many cases, in order to show that the problem is easy, you actually convert it to a SAT problem.
I'm slightly.
Sorry?
I have a few questions about this. So yeah, I did study computer science and took algorithms for this. So a little bit of context there, but what makes it quote unquote easy in practical examples? Is it that there's like a limited number of literals per clause, or is it a limited number of clauses, limited number of total variables? What makes it easier?
That's a wonderful question. And I'm probably not the word expert, but I think I know pretty much a lot about it, and I will tell you nobody knows. But the interesting thing is that none of the things that you say matters. The example that we have huge clauses, huge number of literals. They are actually attempt to make theoretical explanation what make it easy and hard. But maybe you can talk about it later. The idea is that, for example, one intuitive reason is that sometimes it's easy to find satisfying assignment, and sometimes it's easy to show that there are no satisfying assignment. I will answer it later, but there is no easy answer. What I can tell you is that, and you can check, for example, it's very hard. You can take these tools, which are open source, and run them, and it will be very hard for you to find example which it doesn't work.
Question, isn't like the notion of NP completeness mean like all the other problems are like reducible to it? So doesn't that make all the other ones like easy because it's like O of n time to reduce it, if I'm not mistaken? I don't know if that's true actually.
Yeah, it's exactly right. But the issue is that the problem with NP complete or complexity in general, that it tells you about the complexity in the worst case. So it is possible to generate formulas for which this will be hard. It's definitely, but the question is, how do you make them how do you generate them in practice? So it is the case. In fact, many of the people, they use now, if you see one of the usage of these tools that are existing, they solve NP hard problems. So what happened is in Certora, as James said in his lecture last time, is basically we compile the program into a formula. That's essentially what's going on. So we take the program on the one hand, and we feed it to some kind of a compiler with the desired property, and we give a formula to the SAT solver. And the formula has the form something, a formula, and another formula. And this other formula, it's actually a formula that emulates the behavior of the program. So this basically take, in our case, we use the EVM, but you can take solidity, you can take other things. We take a formula that actually captures the precise semantic, the precise meaning of all the statements. And then we take the property that you want, like you have a rule, and we negate it. We take the complement of it. And we are looking for assignment which actually models this formula. And these values that actually represent bug spots. So that's basically, we convert it into a search problem for bugs. And if you give a positive answer, this means we found a bug. If you give a negative answer, we actually found a proof that no bug exists. Okay, so basically this is what we do. We take the program and we convert it into a formula and feed it to the SAT solver.
Question, how exactly, I don't think I fully understand. So you take program P, which is a SAT problem.
The program P is a solidity program or EVM program, whatever. It's a program that's written in a programming language.
Okay, got it.
And go ahead.
Sorry?
Go ahead.
And you have a desired property, which is like you'll never have an overflow for a specific integer or something, right? And then,
usually, no overflow is fine too, but usually we want some higher order property, like some higher level property, like for example, there's no bankruptcy.
Yeah, right. Okay, so you were looking for the truth of this program P exists and there's basically a violation of the property. You write that as satisfiability, and in the, okay, got it. Makes sense.
Yes. Thank you for explaining. So basically, here is a very simple example. This is a program. It has, you see, it's either A is either false or true, and B is either false or true. And then the property that you want to check, that X is equal to 1. So the value of X is equal to Y. So this is converted into a formula. Okay? So you see this formula, the green formula, it captures the meaning of the program. So basically it says if A is true, then X is true. And if A is not true, then X is not true. And similarly, if B is true, then Y is true. And if B is not true, then Y is not true. And then this is the negation of the property. We want to check this for situation that this assertion is violated. So basically it says this assertion is violated if X is true and Y is false, or if X is false and Y is true. Okay? And then you feed it to a SAT solver, and the SAT solver comes with a solution. So basically you see the SAT solver selects for you the path. For in this case, it selected the path that A is false and B is true. Notice this is interesting because it's automatically explore the past for you. Okay, unlike tools like, for example, Slither or other, where we select the past before the tool. Basically, the tool is automatically finding for you the bug. Okay? Of course, it's a hard problem, but all of this is in this SAT query. So basically, it found a bug for you. And if you correct the program, you see, here you corrected the program. So here I corrected this program. You see, for example, when X is assigned to false, B is assigned to false. So it corrected the program. You give the same idea of this SAT query, and now it will tell you that it's unsatisfiable. So here it's even more interesting case because we have a mathematical proof that this program cannot go wrong.
Wait, question. So just to make sure I understand, because I'm not sure I understand. So A is the
Boolean. A is a Boolean. A is a Boolean variable. X is a Boolean. So all of these are Boolean variables. Okay. Later on, we will consider the case that A and B can take infinite values, but A and B are Boolean variables.
Okay, so what you're trying, the desired property is X always equals Y.
Correct. So basically, if X is true, then Y is true, and if X is false, then Y is false.
Okay, so X takes the value of A and Y takes the value of B. Why don't you write assert A equals B? I'm slightly confused as to what these mean in like the context of a language or in context of like proving.
No, if you write something, you can write whatever you want, but the idea is A and B, they are not equal. They represent something about the value. You check if for example, something has some certain values. You can write whatever you write, but if you write A equals B, in fact, it will find a bug for you.
Got it. Okay.
So you write an assertion, and in this case, this assertion holds. Okay, and it mathematically proved to you that this assertion holds. No, good. Ask question. Questions are always great.
Yeah, I'm still slightly confused. So on top.
So this is a program. It checks the value of A, and it checks the value of B, and depending on the value of A, it's assigned X and B to false. Here it's assigned X and B to true, and here it's depending on the value of B. Okay.
Makes sense.
It's a very simple. I'll show you more complex program. But the idea is this reduction to SAT, it gives you both bugs and actually proofs. So in fact, since we are actually using something more general than Boolean formulas, we're using what is called SMT, which is called Start Modulo Theory. And basically, the idea is that the formulas that we write, they can actually be on infinite domains. So for example, the formula X is greater to 2 is also good for these tools. And X can have values which is integer, or Y is greater than 3, or Z is equal to 1 plus 2 times X cubed. This implies that Z is greater than 5. So you can write all of these tools, and in fact, there exist open source, wonderful open source tools, Z3 from Microsoft, CVC4 from Stanford, and other tools. So these tools, they solve a problem which is it's not even NP-hard, it's undecidable. So this means that these
What does undecidable mean?
It means that you can prove that there exists no computer program that solves all instances. So this is a very difficult problem in computer science. It's like the halting problem. It's like these are problems which are very difficult in theory. Okay, so for example, you can write a formula that says Hilbert's tenth problem is solvable. Hilbert is a mathematician, and it's a problem that nobody knows how to solve. You can feed it to the tool, and the tool will time out, of course. Okay? It doesn't, but the idea is that these are very, very powerful tools, and you can try them, and they actually solve millions of variables in seconds. And I will try to give you the intuition how they work, actually answering Zubin's question.
Yeah.
So-
Sorry, Aparna, Kazi.
Oh, so that means the SMT solver can solve like most cases unless it's like an undecidable problem.
Exactly. So in the sense that the problem is, what does it mean undecidable? It's like NP-hard. It means that there always exists an instance of which it will not be able to solve. But if it's not happening in your own program, then you're okay with it. And what we are trying to do, and others, is trying to make sure that it will not happen in many programs.
Okay, so it can solve most programs because most programs are not that instance of like undecidable.
Exactly.
But there exists like a couple of instances which are undecidable.
Exactly. And we can see that actually a lot of things, for example, if you see in your code, a lot of things in your code makes it challenging for reasoning. We'll talk about it. I will tell you. Okay, you have other questions, Zubin?
Yeah, quickly, what do you mean by first order logic formula over theories?
So it means you can write actually a lot of very powerful things. You can write quantifiers. You can write many things here. You can write something like for all value. I will give you an example. It's very, very powerful. The language of these SMT tools solve are very powerful. And actually, they can do many things beyond SAT, which I'm not explaining. They can find explanation. For example, they can find co-ansat. They do a lot of clever things. This is pretty mature technology, actually, which is useful outside formal verification. But I want to explain to you the idea behind these technologies.
Okay, got it.
So one question. So does the likelihood of undecidable, does that like scale with the like number of branches or like the number of possible integer ranges that a value can hold? Does it like scale with that?
So it's interesting. Apparently not. Actually, sometimes more branches make it easier. The thing which is actually hard for these tools is depending on the operation. For example, multiplication is notoriously hard. If you go to exponentiation, it's hard. So basically, it's actually there's something about it. And of course, it depends on the property that you're trying to prove. If you're trying to prove a property which is actually requires deep math, the chances that this tool will need some help by writing axioms like there's no, I mean, it is very, very good actually in terms of scalability, but it's not so good in terms of depth. For example, another case, if you have quantifiers that have complicated quantifier alternation, like I can say for all exist, then this tool can actually have. So when it gets deep in terms of math, then it's when it gets tricky. And actually, one of the things which is interesting and surprising to people that sometimes more value make this problem more tractable. For example, reasoning about reals, it's easier than reasoning about integers, which sounds confusing. I know, because there are more reals, but it's make it easier. It sounds confusing. If you would ask me many years ago, I'd say it cannot happen. Okay. So just to give you an example how this tool works, so you see this is this program. It converts to this SMT query. So you see this is a program in C, but you can do it in Solidity. We work on EVM, it doesn't matter. So you take this program, you see this program has integer and so on. Actually, interesting that in C it's 32-bit integers, but here in the SMT query, it makes it easier that we don't make any assumption. We assume it can be arbitrary integers. And it makes the problem easier. And then we feed it to the tool, and you see the tool automatically find a bug. So it finds a path in which this assertion is violated, exactly like we have seen before. So this is and I didn't explain to you the magic, but before that, I want to show you just one example in smart contracts, so you see that it's relevant for you. So this is a code. And here is an invariant, and I want to ask you like a quiz. So this is a transfer, you have this int 226, and now you are transferring from Aparna to Zubin or something. Is that and the environment that we want to check is that the sum of the balance remains constant. And assume this program has no overflow. We can check for overflow, but let's assume there's no overflow. So is this an invariant? Does this invariant hold?
Oh wait, you said there's no overflows.
I assume there's no overflow. We can model overflow here. We can, but let's assume there's no overflow. You use safe mass there's no overflow.
Okay, assume no overflows. I mean, it looks correct at first glance, but
Wait, you said the sum of the balance.
Yeah. So basically, maybe the in this case there are only two elements which change. But let's assume that
Okay.
we are checking the balance from plus balance 2 before and balance from plus balance 2 after. So
Okay.
are they equal?
it looks right, but I might be missing a bug.
Exactly. So the beauty of
That's
this
how I
technique.
feel.
So the beauty of this technique is, of course, good when you find proof, but it's much more convincing when you find bugs. Okay.
I think if the from and the to are the same address, then it's not correct.
Wonderful.
Oh, this is the BZX bug. This is exactly
Exactly. That's the bizarre. So they could have
Yeah.
used this technology. Yeah. So what happened? We actually modeled it. So we basically converted to the SMT. So this is a bit confusing. So basically what happened, we take the amount which is u into 256, but it turns out that from a reasoning, it makes it easier to assume that it's unbounded. So we actually make it unbounded. It's actually make reasoning. Another thing that we do about balances, we made it what is called uninterpreted function. Maybe it's confusing to you, but the idea is that it's a function from balances. Balances is a function from mass in to mass in. So we don't know anything about this function. We tell SMT you can, and it makes constraint solving significantly easier. So, and then we write these formulas, and basically there is one-to-one. You see that each one of them we convert into equation in a straightforward way. The interesting thing is that here, this is the negation of the invariant. So basically balance from plus balance 2 is not equal to balance star from balance star. And this is a huge search space now, you see, because now all of these from is actually infinite, amount is infinite, balance start is infinite. So we have infinite search space. But this tool will come in seconds. I don't know, actually, sure you can correct me, but I think it's less than a second, no?
It's very quick.
Yeah, so it found this bug. It finds exactly the bug that Highton said. It from is earliest and 2 is earliest, then the amount is 18, then you see that we go from 20 to 30.
So yeah, wow.
Yeah, but that's the beauty of this technique when it finds bugs. Actually, when it proves, it's also good. But it's actually very, very good for disproving, for finding rare corner cases. Especially when you change your code, you went from something to another. So this is the value of this. Okay. So now I want to tell you about, and also, by the way, here is a trivial correction. You see, you can correct the program in many ways, but one trivial way to correct it is just to require that from is not equal to 2, and then you feed it to the SMT. And interestingly, in no time, it will tell you that this bug cannot occur, which is lovely. And it can tell you this for more interesting properties like additivity and other things. So it actually can give you a mathematical proof that something is true. And it's exhaustive. You can, and you say, how is it possible? Because there are infinite number of cases here, but it makes it from a reasoning easier. Okay.
Okay. So on in the SMT query on that side, it's just saying like each of these is one of the clauses, and it's trying to find a value of from and to that cause this to be true. Is
Exactly.
that what it's?
Exactly. You can think about it like a system of equation, or some people will write it as a conjunction. So it's basically trying to find a simultaneous solution to all of these things. And if it found a solution, then it is happy it's displaying it, and we display it in our tool. Or if it finds no solution, it tells you this, there is a proof that this cannot happen.
Okay, that makes sense.
Okay.
So how
Great.
does it find a solution?
That's exactly what I'm going to try to explain a little bit. There are a lot of things I can say follow up, but but I want to show you the thing that I talked to you. I haven't told you anything of what's the magic here. There's a lot of magic, but I just want to tell you that this is a powerful interface. And of course, there's programmable interface. There's a Python interface. There's a lot of things. There's a lot of tools that support by Z3, by others, that get you to, you can actually write formulas in it and use it. And it is used not just for formal verification. Okay, so this is actually the most interesting thing that you can take. So how do you solve this problem? So apparently there is something very interesting which was actually understood already 30 years ago, that looking for a solution is not enough. What we need to do, we search for a solution, and you can think like a blind search, that you can search in depth first search, or search in any way, search the truth value, but you do this and simultaneously you're looking for a proof. And that's actually what gets this thing that it gets it so powerful. So basically, if you give me a formula, I'm trying to search for a model, and I'm trying to prove that this model doesn't exist simultaneously. And this is where things get much stronger and much more powerful. So these two together are much more powerful than each one separately. And the idea is that when you have this search and you are giving this model, it actually prunes the case for looking for proof, because you're only looking for proofs where the search is actually either fails or direct to that. And the proof is also very powerful because it tells you where not to search. And it's very, very interesting together. And actually, this is where all of these techniques work together so nicely. And this is the tools for scalability. So Zubin, you try to ask about when is it easy and when is it hard. So there's a lot of people in theoretical computer science trying to understand. They're studying. And basically what they came up with some solution is that this interaction is what makes such so easy in practice, this interaction is what makes it easier for such solver to solve so many problems. Okay, and there are a lot of tools to that, and it's true in the Boolean case, and it's true if you even more when you go beyond the Boolean case. So this simultaneous search. And the left side, I'm sure you understand, it's like searching for the value. The interesting thing is the right side, which I'm going to explain next. How do you search for proofs? And this work in finite case and infinite case. So far, do you have questions or? Okay, good. So how do we search for proof? So that's actually very interesting. It's a beautiful idea in computer science that came by mathematician in computer science. So Martin Davis is a CS professor at NYU. I think he is in his 90s. And Hilary Putnam is actually mathematician and philosopher. I think he died a few years ago. So they came with this idea which is called resolution, which is a very, very simple idea. The idea is that, and it's beautiful, you can take it to many ways. So the idea is, if you know that A implies B and B implies C, then you know that A implies C. And essentially this is, and its generation, it's called resolution. And you can write it differently. If you say, if you know that not A implies B is like saying not A or B. And if you say not B or C, then from it you can conclude not A or C. So the idea is, from this formula, we can go to this formula. And maybe the last thing is you can write it this way, which is also the same. So this is how we search for proof, and of course we will integrate it with searching for models, but this is how we search for proof. And this proof is going to tell us where there exists no model. Okay, so this is called resolution, and it's based on DPLL if you have, but many things are based on this idea.
Wait,
Later
question.
on,
So,
yeah,
sorry, keep going, keep going.
yeah. Later on, Robinson also actually promoted this idea. There's some programming language based on this idea, like Prolog and others. Yeah, this will be.
So how does this so this is just like the notion of like, you know, just like you have a syllogism here. How does this connect to making proof finding easier? Or like, how does this connect maybe to the searching process, proof searching process? I still don't.
So I'll show an
Cool.
example in the next slide. Maybe it will
All right,
be
cool.
easier.
Awesome.
So let's see that on Boolean case, but it can work actually in first order. It can work in many things. So let's see that in Boolean case. So somebody gave me this formula, okay? And you can think about this formula as a system. So basically this says A or B or C hold, and B or not C and not F, and so on. It could be in infinite case, but I'm in a finite case. And what I'm going to do resolution. I'm going to find consequences. And I'm going to do it variable by variable. So the first thing, I'm going to take B. And you see that here, I resolve B here with not B. So basically, I know this formula holds, and I know this formula holds. And so with this resolution, I conclude that it must be the case that either A holds, or C holds, or E holds. And similarly, I take the B and not B here again, and I conclude that not C or E or F. So basically, I just take all the remaining propositions, and I conclude that they must hold. And then I take again here, I resolve C and not C. So I find out that this is the case that A or not E and not F. And this procedure is terminated. And now what I can say, this formula must be satisfiable. Because it's easy to find out it's satisfiable. Just pick a value. For example, you take the value E is 2 and B is 2. And you see that, in fact, in this procedure, in this procedure, you see, it's actually kind of linear. You basically, every time you take a variable and you do this elimination. And you can do it. You can do it in general. Maybe I give you another example more interesting. So you see, I took this more complex formula. And once again, we resolve B and not B. We get A. Here, we just copy the formulas. Now we resolve A and not A. We got C. We resolve A and not A. We got not C. We resolve them together. What do we get? Contradiction. It's actually, for us, it's good. You say zoom in like this because we found out that this program does not have bugs. We found a proof that these things cannot hold together. So if this would be the open shares updating something, and this would be the solvency, this will say the solvency cannot be broken. And this is unset. So this is beautiful. This procedure is beautiful. You can search for proof and notice that this is actually pretty easy to implement. You just pick a variable and you do that. And it's quadratic, whatever. You basically do this. It's very easy. So why is it not so? Why can't we just implement it and run it? How can we say this problem is NP-hard? Why can't we just search for proof for all programs? What's the problem? What's wrong with this procedure? It's not wrong, but where can it get hard?
If it's not able to reduce it.
No, but if it's not able to reduce it, then it's in fact sad. We are happy. And if it's able to reduce it and it gets the empty, then it's unsad. And we're also happy.
Oh
So
no,
what-
I'm saying like in this case, you're able to get rid of B and not B, A and not A, right? But what if there actually wasn't
Yeah,
a
so,
way to
so
get rid of it?
earlier, we have seen there that in fact, we were not able to reduce so far, so that's good, because it says this formula is satisfied.
Okay.
So why is it so? Why can we just get done? Why can't we just solve this problem? So it's very nice. This is, I guess, Davis and Putnam procedure, but why is it? Why can't we just run it and find all the solution? We basically run it and do this resolution. Every step we basically enumerate the variable. Every step we eliminate one variable. What is the problem?
Hmm.
So the truth is that, in fact, it's fine, but this procedure can explode, because I haven't showed you examples. There will be examples where there will be too many resolvements. There will be too many cases. There will be too many conclusions. That's the problem. In practice, there will be too many conclusions. If you run it on a real program, there can be a lot of things that you can conclude. So this actually makes it exponential even in space. It will just explode. So what we want to do, we don't want to search for proof. We want to search for proof and model together. And that's the idea. They are searching for these proofs together with the model. And the model is very simple. You just enumerate. For example, you select the value of A to be true and you check it. But the idea is you want to run them both together, because this is the way to avoid exponential explosion, to avoid the fact that they will explode.
So what do you mean by that? Do you have an example of something that'll give you lots of different
Yeah, I didn't prepare an example. I think it's tricky, but the idea is that if you have like this variable occurs here, and then it occurs in other cases, then each two of them, and the idea is their lengths also will get longer. Okay, so the here is the case that every time you did, or actually maybe in the previous one, there were examples where I resolved no. But there will be cases when you resolve two formula and you get another formula which is larger. And then after you resolve it, you get another formula which is even larger. So it gets more and more complex, and it makes the reasoning harder.
I see.
I can, maybe you can try, or I can try to send you examples for which this happens. So if you ask where are these things that these solver can have hard time, these are the cases. And what we do, we combine this proof search with model finding, with basically finding models. Or maybe you can say just case splitting, just basically looking on a case by case, whether the value is A of 0 or 1, and so on. And also, by the way, if you have nonlinear, this is also what we do. If you have a solution which is complex, we just do case splitting. Okay, so this is the idea, and it's actually working pretty well in practice. You can try, but it's working pretty well in practice. And it's extended by in many cases. So these are a lot of cases. There are a lot of cases that we know how to handle. And this is one case. So there are a lot of cases that we know how to handle. And there are, of course, many cases that we don't know how to handle, that things get more complex. So for example, linear arithmetic, we know how to handle all kinds of things that we know. And it's interesting because some of them is infinite. So maybe I give you one example just that you see that the value. So here is a very, very simple case, which is very nice to solve. So basically, these are called difference constraint. So you have two variables, and you are saying that their difference is less than some constant, where constant is a value that you know. So this is very useful in scheduling in many cases. But you notice this is a very limited cases because you only have two variables. And this makes reasoning very easy. So basically, notice again here, we are not assuming any value here. We are X and Y can take arbitrary value. And so is C. But C is known, and x and y are unknown. Okay? So how do we solve it? So here is a simple example. Somebody gave us this equation. Is this equation satisfiable? What do you think? Can we solve all of these equations together? It's x and y are integers, and w.
Yes, it looks satisfiable.
Looks like we're gonna have an issue with the last two inequalities.
You got it.
Yeah.
Wait.
So how do we find out? So we, of course, can enumerate the solution, but that's not what we want. We want to do. I mean, it's enumerate all integers, right? So what are we going to do? So the first thing we do is it's simple, but we normalize it. You see, we basically just write it in these inequalities. So basically here
Yeah.
we added a variable z0, which is equals to 0, and this one here there was inequality of this side, so we basically make it in the equality that we want. And then we convert it to actually graph, which is called constraint graph. So the variables are, the nodes are variable x, w, y, and z. And basically when there is a constraint, we just write it as an edge. So basically this says here x minus y is less than 5, x minus w is less than 1, w minus x is less than minus 2, x minus z0 is less than, we convert it into basically a graph. And here the problem is solvable because what we know now, this formula is satisfiable if and only if you don't have negative cycle. So basically this formula is not satisfiable, and this is what Michael observed, because there is this negative cycle that you go from here to here, and the value of it is 1 minus 2, which is minus 1. So here you can solve efficiently this case, even though, and there are a lot of cases where we can solve things efficiently. So this is a case when we can solve things efficiently. And we can solve it for many variables, as long as there are two variables, and in fact, these variables is infinite, it makes reasoning easier. Okay, so,
Oh, yeah.
Sorry?
No,
Sorry?
nothing. I don't know why I didn't see the last two blatantly
Okay, no
contradicting
way.
each other.
no, but it can be hidden. Of course, I wrote it, but the idea is it can be hidden. It can be a fairly complex equation. And then the question is, it's satisfiable. And these tools are able to solve it. So basically, these tools, they implement these procedures, and even more complex procedures. Here is another case.
So in the previous case, we're just saying that it cannot be solved, right?
Exactly. And if they want, and it's if and only if, in the sense that it gives you a sufficient and necessary. If they can be solved, in fact, we can just run shortest path algorithm and find the solution. So basically, algorithm that find the shortest path, whether it's Floyd or whatever, you can write this kind of algorithm, then they will use it. And in fact, these SMT solver, they have a lot of algorithms implemented in them, shortest path and others that actually do all of these clever things.
Oh, that's so cool.
But the interesting thing, you see, they never enumerate X and W. This will never work. And they never enumerate the branches in your code, because actually the branches in the code is converted into a Boolean formula. So in fact, and this really pays off, because we can handle programs with many passes this way, and with loops and many other things, which actually is possible. Okay, so we can do other things. So another case which is interesting is uninterpreted function. I guess this is a bit confusing, but we have seen it in the example of the balance. So what is an uninterpreted function? It's like function in solidity, but we don't take into account any of the property that it has. So basically, you can think about it as basically a pure function. It's something, and the only axiom that we know that if x is equal to y, then f of x is equal to y, f of y. And we can solve these things pretty efficiently. There is an algorithm which is almost linear that we can solve these cases. So basically, here is a case that we can go with huge number of variables and solve things efficiently. It gets more complex when you have complicated arithmetic, especially on the integers. Interestingly, in the real, it's still decidable, but for us, because we care about smart contract, we want to prove things about integer. We are not actually handling real, even though they may be easier. And here is a case that we have this Presburger arithmetic. So this is a case that you really have math. So you have a mathematical equation, and you have also quantifiers. You see, you can write something like induction principle, that if you show that the property holds on 0, and then if you show that if it's hold on x, it's hold on x plus 1, then it must hold on all integers. So this gives you pretty powerful claim. So for example, we can write this formula that says that for all x, for all y, if x is greater than 0, and if y is less than x, then y plus 1 is less than 2 times x. Is this formula true? The quick guys?
I did not understand what is happening in this slide. So what is this slide saying? Is it saying that
It says that for all the values that, for all, if the left-hand side is true, then the right-hand side must be true.
Question. Wait. Maybe I missed something. Wait, I don't actually. Is there any constraints on what? No, x and y is all reals, right?
Integers. If they're real, it's
Oh,
easier.
integers. Okay.
Integers, but it's still infinite.
Yeah. And then x is positive, y could be negative. Yeah, I mean that. Yeah, this can hold. An example.
It holds.
I've been wrong too many times.
You can, by the way, there is Rise for Fun. There is a website where you can try all of this. Microsoft put this website, which is actually you can try all of this.
It doesn't always hold, but
No, but if it so this is verification. If it doesn't,
Right.
find me a counter example. If it doesn't hold, find me a counter example.
Got it.
I think it's okay, actually.
I think it.
I think the only number you should worry about is 1, and 1's okay.
Okay, so the idea
X
is,
equals
again,
1.
we feed it to the SMT. So you see the idea is I took the formula, I took its negation. So this is the negation. It's basically say x0 and is greater. I didn't write the conjunction, but it says x0 is, so x0 is the one which is, and it's greater than y0. And here I take the negation of the conclusion. So basically the consequence, and I give it to the SMT, and Z3 quickly say answer. So it's
All right,
fun.
so there's an issue.
Sorry?
Unsatisfiable means
It means that there exists no solution.
no contradiction. Yeah. Okay.
Yeah.
Not possible.
Yeah. So that's pretty cool that it can do this kind of things. It's pretty cool that it can find these kind of things. I can tell you the story when it gets more complex. It works well when you have linear arithmetic, but when you go beyond linear, it's tricky. It's not. I don't want to tell you that everything is easy, and then you run out of time. You have timeout, and you complain to Shelly. So because there are actually cases where it gets hard, and people are improving that. Actually, the Stanford team, CVC4, Microsoft team, the Yikes team, actually SI, they are all actually within a few miles from you. But they're all working on improving this kind of constraint solver. There's annual competition. Actually, we contribute example to that. There's a lot of things getting there, but it can be hard. And of course, scalability is also an issue. If you have millions of variables, it can also make things hard.
So Muli, it's really just because we're applying the induction step that we are basically making a statement about integers and not real numbers.
It's the induction which makes it an integer.
Yeah, like I'm just wondering, like when have we said that we're gonna check this just for integers? It's because we're applying this induction technique, right?
Yeah, so you're saying two things which I should be careful. Thank you, Michael. So one thing is that the induction requires that it will be on integer. But when I work with the tools like Z3, I do tell him, I tell him that it's integer here. Okay, so there are two things that you're saying which is correct. I have to tell SMT which type is the variable, and I tell him it's integer. And if I tell him it's integer, then in fact, it makes reasoning harder, but I have to tell him that it's integer. And you're also right that if it's integer, then induction principle occurs. And in Presburger arithmetic, the interesting thing is that this is still decidable. It's still, it is guaranteed to give you an answer on arbitrary formulas. Does it make sense? I'm not sure I answer correctly.
Yeah, that's okay. Like, what if in this case we were wondering if this is true, not for integers and not for like all real numbers, but for like certain like predefined fractions, like say in our system, like we can divide down to like 1/100 or something. Does that make sense? So like if that were the case, this would not be true, right? And we would still be able to use the induction technique.
So you're saying you want to apply induction, but not on
Yeah.
integer.
Yes, on like predefined number of decimals, right?
Yeah, you could, because basically what you do, you define orders, and then you could do this. We can, I mean, it's not something that our current tooling supports, but there's in principle in math you can do that. You have, as long as you have a well-defined order, you can define induction on it, and then you can prove things by induction. We can actually prove some decidability here. It's not something that the Satora tool handled, but in principle, there's a lot of techniques that not all of them are integrated into Z3, and this what you could reason about things that are on induction, which is not just integer. I mean, actually, Z3 already have inductively defined data types and some things that you can reason about something similar, but it's not supported in the Satora tool. But yes.
Okay, thanks.
Okay, so I think I'm almost time. So I want to tell you there's a lot of excellent material. There's courses. There's actually annual course in the Menlo Park, not very far from you. There's a lot of material on the internet. There is, of course, Wikipedia. There are surveys by the Leonardo Mora and Nikolai Bjorner. There is by the CVC4 team. I also pointed one work.
Oh, your papers.
Yeah, one of them. I didn't want to pollute too many, but I work on a specific thing, which is basically infinite things. But this idea of games, this I think it's explained well in this idea of this interplay between the prover, the game between the prover and the one who's finding the model. I think it's actually explained nicely in this paper. Maybe I just summarize. So I think these are powerful tools. It is true that I only sort of touched the surface of it. They're used in many contexts. We talk about formal verification, but tools like Slither, they also use SMT synthesis. People are synthesizing. They are trying to find solutions using SMT. So instead of trying to find bugs, you're trying to find a fix. You're trying to find a case that you want to find a configuration for your system for which something holds. So this is a case which is used. And also optimization. In terms of challenges, there are a lot of things I didn't describe, and some of them are related to what we do in Satora, like handling low-level memory. We are handling the bytecode, so that's make it harder. Reasoning about relational property, comparing two programs, reasoning about higher order function like sums, and we have goals that we are integrating. Reasoning about data structures, about loops, how do you write invariant, and reason about connection between contracts. So all of these are interesting, and I think James said maybe he will talk about some of these things later.
Cool. This was awesome.
Yeah,
Does
this
anyone
is
else
super,
have to?
super helpful.
I mean, I'm sorry, it's a bit technical, but you asked for that.
No, technical's
No,
good. I
don't
think
be like
no,
it.
technical's good. Technical's good.
Yeah.
I think there's some parts in the earlier parts that I'm still like not 100% wrapping my head around. Actually, can we go to yeah, here. I think like I'm still stuck on a Parnas question and like would love to understand more as to like the exponential like blow up and like what causes that. Cause I think so in the previous case, like if we go to the previous slide, we find that it's satisfiable because it's like A or E or like not F, right?
Yeah, basically that we couldn't find, basically maybe the thing to, maybe I should have explained, and maybe Alex can, this is basically like proof by contradiction in some sense. You did not derive a contradiction. Some people call it usually refutation. And since we were not able to derive a contradiction, we say it's correct.
Yeah, you should
So
say
when I
that you have
explain-
done all possible resolutions, right? Otherwise, you can't say that.
Exactly. Yeah, thank you, Alex. So the
So
idea
is
is
it-
this
yeah,
procedure,
sorry, keep going.
yeah, go ahead, Zubi.
So is it that the exponential blow up is that like after going through what is it called? The
Resolution.
resolution process, you end up with a satisfiability problem that's just like still too large. Because is that what it is, or what is it?
You want to answer, Alex? Go ahead.
Yeah, I mean, in order to finish, either you find a contradiction, right, in the other example, or you have to do all resolutions. And all resolutions are, that's exponential thing. So I think essentially every step can be quadratic. Think that half of your formulas in the input have variable a positively and the other half has it negatively. Then you have to, for each group, have to do each with everyone, right? So that's quadratic. And in the next step, the same can happen essentially. And so you can have number of variables, many steps. So the number of resolutions of resolvents is exponential. Does that make sense?
Yeah, I understand intuitively why the number of resolutions is exponential in size because like, wait, do you mean that there's like 2 to the n possibilities? What do you mean by the number? Can you walk me through that again? Like what the number?
So
of resolutions
basically,
is?
in this case here, there were 3 formulas, and basically these 3 formulas they gave 2 formulas to the procedure, and then but what Alex is saying is that if you write your formulas in a different way, from 3 formulas here, you can get many more things, because from each, and also the size will get longer.
So it can be more rather than less, right? So each line can be bigger than the previous one.
The previous line.
Yeah.
In terms of how many clauses you like.
I get what you mean by
I see.
quadratic. I get what you mean by quadratic because like you have like you have to check for like 9 different like connections per thing, and then there's like n different things, and so it's okay.
Yeah. So one example
clause,
where it really happens in practice, especially in the infinite case, if you have a transitive relation, you say if x is equal to y and y is equal to z, then x equals to z, and then it just tries to get more and more. You will see this, and this actually happens in practice. So that's why you want to connect it with model finding, because the idea is this resolution, and by the way, there are great resolution too, like Vampire, which is open source, but they still have a very clever way where they try and actually how to basically order this resolution so they avoid this explosion. So basically they are trying to say which resolution is more important in order to get a contradiction, because the goal of the proof is to find the contradiction fast, and the goal of the model finder is to find the model fast, and they actually help each other. Okay.
All right, awesome. I think that's time. Don't want to keep you guys. Happy New Year. Thank you so much for this. Really appreciate the time. I'm gonna dig in and learn a little bit more, and we'll do some.
Yeah. feel free to ask questions. And all of these guys are also our friends, and they also can talk to you. Yeah. Thank you. Happy
We
New
love
Year.
it.
Thanks
Yeah.
for the
Yeah,
time.
happy New Year.
Thank you.
Also,
Thank
if there's,
Happy
yeah,
New Year.
would love to
Happy
do
New
another
Year.
lecture, like
Sure,
on
sure.
whatever the next, like,
I think they're
Yeah.
planning that. Thanks a lot.
Right. And,
yes.
and always happy to do one on options or finance if you guys are interested. Just let us know.
Okay,
We
wonderful.
can
Cool.
do that.
Yeah,
All
yeah,
right.
yeah. We want to get that actually. We are interested.
Okay, okay.
Andrew, yeah, we have you. Yeah.
Sounds
Let's
good.
do it. All right. Awesome.
Bye.
All right. Thanks. Bye.
All right,
Bye.
bye.
Nice New Year.
Bye bye.
Bye.